Okay, good afternoon. So today we're going to hopefully get the real-time systems lectures done and move on to memory translation. Now, for some reason, I cannot give you video today from my camera, so we're going to just look at the slides. Now, I'm jumping over total bandwidth servers. So I'm doing that for the interest of time. So this topic, the topic of the topic of total bandwidth servers wouldn't be covered or wouldn't be included in any of the exams. So we're just jumping over it. Okay. So let me actually jump over it. Okay, so the next topic that we're going to talk about with regard to real-time operating systems or real-time systems is the issue of synchronization, task synchronization. So, so far, EDF, monotonic scheduling, rate monotonic scheduling, and least laxity first scheduling, all of the scheduling policies that we talked about, the main assumption was that the tasks are independent. So there was no dependency considered when we were scheduling tasks. So we will look at each task independently and jobs within the task independently, and then we would schedule them. In real systems, that's not always the case. So you have the cases where your tasks and your jobs are interdependent. So it could well be that one of the jobs or one of the tasks acquires a lock, and the other ones might want to access that lock. It could well be the case that as you will be implementing in P3, tasks might want to send each other messages, and they might have interdependencies. So in general, deciding if a set of dependent tasks are schedulable is NP hard. So if you have dependencies between tasks, meaning that if execution of one task depends on execution of another task, then making a decision to see if a set of periodic tasks are schedulable or not is NP hard. And for those of you who are familiar with this basically, so informally, not necessarily exactly, but informally means that the size of the problem grows exponentially with the input size. Now, the implementation that we saw in multi-threaded kernels. So if you remember about the lectures where we talked about implementing semaphores, condition variables, and mutexes, that was a general purpose implementation that works well with general purpose operating systems. If you apply the same implementation, if you use the same mutexes, the same semaphores, and the same condition variables for your real-time tasks, it might have implications that are not desirable for your system. One of this, actually the most important implication is priority inversion. We have seen priority inversion 2 times so far, and in both cases I told you that we'll talk about it in details when we start talking about real-time systems. So here it comes. What is exactly priority inversion? So here's an example of a scenario where priority inversion happens. So let's say you have a low priority task, a medium priority task, and a high priority task. Now let's say your low priority task acquires a lock. So let's say we're locking this mutex R1, and let's say at some point a high priority task comes in your system and it wants to acquire or lock the same mutex. So at this time, when it tries to do so, it's going to get suspended, as was implemented in our mutex implementation. So the high priority task is going to be blocked by a low priority task. So far, it's kind of so good. It's not preferable, but okay. So we're going to let this go. But as you will see, this is going to lead to something even worse than the high priority task being blocked by low priority task. Now, at this point, we're going to come back, start executing the low priority task. And let's say at some point a medium priority task comes in. Now, the medium priority task is going to preempt the low priority task and run. Now, what is happening here? So what is happening here is that this high priority task, which was initially preempted by the low priority task, is now waiting for this medium priority task to run. And once that medium priority task is done, the low priority runs. And finally, once the low priority task releases its lock, then we can go and run the high priority task. Now, if I didn't have this medium priority task come in, if this medium priority task didn't come, then I would have finished the low priority task here, and then I would have gone to the high priority task here. But because of this medium priority task, I had to delay my high priority task. And this delay is what is called priority inversion. So what is happening is the high priority task, which was supposed to run at time 10, is now running at time, let's say, 13 or 14 or whatever. So I don't exactly know, like whatever the size of this medium priority task is. So basically this medium priority task, which does not even touch this mutex, which does not have any resources in common with high priority task, is able to delay the high priority task. So maybe this delay was the delay that caused by low priority was justified because low priority task had the mutex, but this delay by the medium priority task is not justified because the medium priority task didn't even have the mutex. And this is called priority inversion. Now, this in a real-time system is going to be detrimental because if I care about the execution time of my high priority task, now its execution time depends on the arrival of the medium priority task. If I have a medium priority task show up in my system, then this high priority task is going to take longer time. And this is basically unpredictability being added to my system, which is absolutely not desirable. Now, there is a real case that this happened, so I'm not going to spend time going through this because I'm running out of time for this. But if you're interested, you can actually look at Mars Pathfinder that was sent to Mars in 1997, and a real case of priority inversion happened, and it led to a loss of data and a lot of trouble for NASA with their Pathfinder. So again, I'm going to just jump over this as well. So if you're interested, just look at the example in this slide. It explains what the problem was, but in essence, it was just basically priority inversion causing the system to crash. Okay, now how can we get rid of priority inversion? The first solution to eliminate priority inversion is a protocol called priority inheritance protocol. So what this does is every time a task blocks another task because it's holding a resource, it inherits the priority of the blocked task. So let's run this in the example that we saw. So if, let's say, a low priority task is running and then it locks a resource, and then a high priority task comes in and tries to lock the resource. Now, oh, so this slide is showing the problem with this. The problem with this is deadlock. Let me go back to this example here and show show priority inversion in action. Sorry, priority inheritance in action. So going back, so at this point, the low priority task has locked the mutex. Then high priority task came in, and at this point, high priority task tried to lock the mutex, and it got blocked. So at this point, we come back to this low priority task. What is going to happen with priority inheritance protocol? We're going to enhance the protocol, the priority of this low priority task to high, because this low priority task blocked a high priority task. Therefore, it's going to inherit its priority. So the priority of this low priority task is going to change to high because it has blocked a high priority task. And you can see why this is important, because then when the medium priority task comes in, I'm not going to switch to the medium priority, because now this low priority, the priority has changed to high. So if a medium priority comes in, I'm not going to stop the running task to switch to the medium priority. I'm going to continue running the low priority task that has now inherited the priority of the high priority. And by doing this, we're going to prevent priority inversion. Now, the problem with that is it could cause deadlock. So here is an example. So I have low priority. Let's say it locks resource 1, then high priority comes in and it locks resource 2, then tries to lock resource 1. So if this happens, now the priority of this low priority is going to change to high because it's going to get blocked. So this high priority is going to get blocked. So we're going to go back to the low priority. And now I'm changing the priority to high. And now if this guy tries to acquire resource 2, now I have deadlock because I have two tasks with the same priority that they're waiting for each other while holding the resources. So this leads, this PIP protocol is going to lead to deadlock. The other problem with PIP is that it's not going to prevent chained blocking. It's going to prevent the blocking that we saw in the first example. But look at another example here. Let's say I have low, medium, and high. So low is going to lock resource 1, then medium is going to come and it's going to lock resource 2, and then it's going to lock resource 1. At this point, I'm going to change the priority of this guy to medium because it blocked the medium priority guy. And I'm going to continue running it until a high priority task comes in. Now, if this high priority task tries to lock resource 2, so this is the resource 2 that was locked by M, then it's going to be blocked by the M priority, and we're going to come back to the low priority. Now, this is indeed chain blocking. Why? Because if you look at high priority task and if you look at the low priority task, what is the relationship between these two? Well, these two are independent because high priority needs R2, whereas low priority only needs R1. So H and L in this case are independent, at least at the surface, right? Because they need different resources. Therefore, it doesn't make sense for us to block high priority by the low priority. So since we are blocking, this is bad. So this is not priority inversion exactly, but it's this one is called chained blocking. And why do we have a chain? Because M1 is blocked by L, and now R is blocked by M, which is blocked by L, so H becomes blocked by L, which is bad. Okay, so an alternative that addresses all three issues, so an alternative that addresses priority inversion, deadlock, and chain blocking is called priority ceiling protocol, PCP. So how does this work? This is a combination of the bank's algorithm that you saw in 252 and priority inheritance. So it's a combination of the two. Obviously, we want to deal with deadlock, so we have to have some notion of deadlock prevention algorithm here. So the way it works is each resource is going to be assigned a priority ceiling. Now, what is this priority that we're going to assign to each resource? It's going to be equal to the highest priority of any task that can lock this resource. So here, right here, let's pause. This assumes that we know upfront what tasks are going to request a particular resource, and we're going to assign the priority ceiling of each resource to the highest priority of any task that can lock it in the future. Now, each task can only lock resources that have a priority ceiling that is less than the priority of the task. So if a task with priority low tries to lock a resource with priority ceiling M, then it can't do it. That request gets denied. Of course, this has to be for only the resources that are currently locked by other tasks. So if you have a resource that is not locked by anyone, then you don't look at its priority ceiling. But if you have a resource that is oh, I'm so sorry. So if a task with priority low tries to unlock a resource with priority ceiling M, then we're going to look at all the resources that are locked and see what their priority ceiling is. If all the resources that are locked have priority ceiling L, then we allow this. Or if no resources are locked, then this is basically 0, so we allow this. But if there exists a resource with priority ceiling H or M, then we're not going to allow this. So we're going to prevent this request from being answered or being satisfied. Similar to priority inheritance protocol, if a task blocks another task, it inherits its priority. Now, PCP prevents deadlock. So if we look at the example that we had before, let's say I have L and H. So L at this point wants to lock R1. It can do that because at this point no resources are being locked. So the highest priority ceiling is basically 0. So L can lock any resource it wants. So let's say it does that. Then the high priority comes in. Now, let's say high priority task wants to lock R2. What is the ceiling of R2? So the ceiling of R1, first let's talk about the priority ceiling of R1. The priority ceiling of R1 is H, because R1 is a resource that H eventually wants to lock. So the priority ceiling of R1 is H. Okay, what is the priority ceiling of R2? The priority ceiling of R2 is also H, because H wants to lock that resource. Now, if H wants to lock R2, I'm going to look at any resources that are currently locked. Well, that one resource, there is only one resource that is currently locked, and that's R1. Then I look at the ceiling of R1, which is H, and then I compare H with this H. Because the priority of this task is not higher than H, it's equal to H, so it's not higher. Therefore, I'm going to deny this request. So this request gets denied, and H gets blocked. We don't allow H to lock R2. We go back to L, and we increase the priority of L to H. Then let's say yeah, the other thing here that is important is this other tasks. So we have to look at all the resources that are locked by other tasks, not the current task. So at this point, when L tries to lock R2, we're going to look at any resources that are locked by other tasks. So there are no such resources. There is R1, but R1 is locked by the current task, so that doesn't count. We're going to look at resources that are locked by other tasks. In this case, there are no such resources. So then L can also lock R2 and finish. Once it's done, then we can go to H and continue H. And as you can see, we have prevented deadlock. And this basically is very similar to the ideas behind the Banks algorithm, because we're preventing deadlock by not allowing H to lock R1. Okay. PCP can also prevent chained blocking. So look at the same example we saw previously for PIP, where chain blocking was happening. Let's look at the same example. So L runs, it tries to lock R1, it can do that. Then M runs. Now M wants to lock R2, but it cannot do that because this R1, the priority ceiling of R1 is M, and M is not higher than M, so M is not going to be allowed to lock. So L continues running, then H starts running, and at this point H can indeed lock R2 because the ceiling of R2 is so because it's going to look at all the other resources that are currently locked. The resource that is currently locked is R1 by others, and the priority ceiling of R1 is M. Now H is higher than M, so H can indeed go ahead and lock R2. So, oops, sorry. So this prevents chain blocking, because chain blocking was happening when this M was able to lock R2, and then H would get blocked by M, where M was blocked by L. Now, in this case, H is not blocked by L, so H can run without getting blocked by low priority task, which is what we wanted, right? Because if I look at H and L, they don't have any dependency. H only needs R2 and L only needs R1, so L should not be able to block H, and that is happening. So this PCP is able to prevent chain blocking. Okay. Now, this idea of priority inheritance can be applied to scheduling policies like EDF, right? So the same idea that, you know, if a low priority task can block a high priority task, it inherits its priority. We can do the same thing with deadline, earliest deadline first. So in EDF, the deadline of each job is its priority. So if a task with the highest deadline, meaning a deadline that is coming far in the future, is able to block a task with a earlier deadline, then it can inherit the deadline of the task that it has blocked. Basically, inherits the deadline of the task that has an earlier deadline, and that would boost the priority of the task that just blocked the other task. And now we are able to run this task to completion and allow the other task that got blocked to run after that. So this idea of, you know, priority exchange or inheritance can be applied with deadlines. So we can use deadlines, tasks or jobs can inherit each other's deadlines if they can block each other. Okay. Now, the other, I'm actually going to, let me see, what are the other topics on? Okay, so I'm going to briefly talk about real-time systems running on multiprocessors. So we saw that even with general purpose systems, running the system on a multiprocessor introduces a lot of complexities for the operating system. Now you could imagine all of those plus extra complexity if you run your real-time system on a multiprocessor. So here's one example of a complexity that will be added if you have a multiprocessor. This is called so here is an example of remote blocking in multiprocessor. So this doesn't exist in a uniprocessor, but the moment that you have a multiprocessor, you can have remote blocking. So here is the example. Let's say you have two CPUs, CPU1 and CPU2. CPU1 runs two tasks, a low priority task and a high priority task. Now assume that low priority task locks R1, and then it gets blocked by a high priority task until it gets to run again later on, and then eventually it unlocks R1. Now, this is fine, and nothing special to look at here. But what happens if CPU2 was running a medium priority task? So if a CPU2 runs a medium priority task, and this medium priority task wants to acquire R1, let's say R1 is a mutex that medium priority task wants to lock, what's going to happen? Well, the lock is acquired by this low priority task, and this low priority task is blocked. So at this point, this medium priority task is going to also get blocked until later on when the low priority task eventually runs, and then this medium priority task is going to run next. So what is happening is that this high priority task is kind of remotely blocking this medium priority. And this should not happen because I have a multiprocessor, right? So if I'm assigning the high priority to the CPU1 and medium priority to CPU2, they should both run. But because of the dependency between L and M, unfortunately, the H is able to remotely block M, and basically this time is wasted here. It could have been avoided. And the way to avoid this is to just allocate this low priority task to CPU2 so that it just gets blocked by M, and H can run independently from M and L. So this is one example, right? There are so many others. Now, similar to multiprocessors, scheduling real-time tasks on multiprocessor is going to be challenging. Now, the domain of schedulers gets divided based on their capabilities. Now, depending on if you allow migration or not, you might have two different classes. One allows migration, one doesn't allow migration. If you don't have migration, this means that tasks are assigned to certain CPUs. So if you remember about CPU affinity, we're going to set the affinity of each task to a certain CPU, and we're not going to move them between the CPUs. So that's that. Now, you could have restricted migration, meaning that you could say, I'm not going to migrate jobs, but I allow different jobs from a task to be assigned to different CPUs. So in the first one, a task gets assigned to a CPU, therefore all of its jobs are also going to run on that CPU. In the second one, in the restricted migration model, I'm not going to assign each task to a certain CPU. I will just assign each job to a certain CPU, but then I don't allow jobs to migrate. So this allows each task to run on different CPUs, but jobs cannot migrate. So different jobs from the same task could run on different CPUs. But each one of those jobs can, once they're assigned, they cannot move. And finally, I have the full migration that would allow jobs to also migrate. So a job could run half of its execution on CPU1 and then migrate to CPU2 and finish on CPU2. So these are three types of migrations that you could imagine supporting, right? Depending on these three types and the three types of priority assignments. So if you remember, static would assign same priority to all tasks, to all jobs of the same task. Dynamic would allow each task to have its own priority, but then the priority wouldn't change over time. And then fully dynamic would allow each job to have time varying priority. Now, so this is for priority. And this axis is for migration. So this gives us 9 different classes of schedulers. So you can have a static scheduler with no migration, a static scheduler with restricted migration, a static scheduler with full migration, and so on and so forth. So I have assigned S for a static, D for dynamic, F for fully dynamic, no migration N, restricted migration R, and full migration F. So this FF is the most flexible scheduling you might have, where the deadline, the priority of each job could change over time, and also each job could run on every CPU in your system. They can migrate between CPUs. Now, unfortunately, I don't have much time to dive deep into all the details of all these classes of scheduling, but just to review some of them. So all the no migration classes. So if you do not allow migration, meaning that you're going to fix tasks to CPUs and all the jobs from the same task are going to run on the same CPU, then you can show that finding optimal assignment, so an assignment that meets the deadlines with this scheduling policy, is going to be NP hard. So finding a schedule that is feasible is going to be NP hard. And this doesn't depend on how you're setting the priorities. So no matter how you set the priorities, if you don't allow migration, then finding optimal schedule, a feasible schedule, is going to be NP hard. Now, there are several polynomial time heuristics for this. So one is first fit. This is very similar to the first fit memory allocation that you had. So for any task that comes in, you find a best CPU, the first CPU, sorry, you find the first CPU that can run this task without missing its deadline, and then you assign that task to that CPU. And that would depend on whatever scheduling policy that you're using. So depending on what this first piece is, you look at your feasibility constraints and you assign the task to the first CPU that can run it. Obviously, this is heuristic. It might not produce the best schedule. The second one is a best fit. So basically, you find the CPU that can accept this task, but you want to also for this task to have a minimal remaining sparse capacity. So you sort of want to assign this to the CPU that has the lowest load, the lowest utilization, so that the remaining capacity that you have in your system is minimized. You can show that the worst case utilization that you can achieve in your system is m+1 divided by 2. Now, what do I mean by this worst case utilization? So if you have m CPUs, let's start with one CPU. If you have one CPU, what is the highest utilization that any task scheduling can give you? So if you remember EDF and LLF, least laxity first and earliest deadline first, both of them can support utilization of 1. So if your task set has a maximum utilization that is less than 1, then EDF and LLF can schedule them on a single CPU. Now, if you have 2 CPUs, you're hoping that you could run a task set with maximum utilization that is less than 2, right? Because each CPU can handle utilization up to 1. Now, if I have 2 CPUs, I should be able to handle utilization up to 2. And if I have m CPUs, I want to be able to handle a task set with total utilization of m. Because I have m CPUs, each one of them can run utilization up to 1. So m times 1, that's m. I'm hoping to achieve m. So that's what we want to achieve. That's the best case scenario. You can prove that if you don't have migration, then the worst case utilization is m+1 divided by 2. So basically, there are task sets with utilization m+1 divided by 2. So this is basically 50% utilization. right? Is if M is 10, this is going to be 5.5. If M is 20, it's going to be 10.5, right? So, which is half of your capacity. Your capacity is 20, but this bound is 10.5. That's about 50%. So you can show that there are task sets with M plus 1 divided by 2 utilization, total utilization, that cannot be scheduled on a system with M CPUs if you don't allow migration. And it's easy to see. I'm not going to spend time to prove it to you, but basically this shows that preventing migration is going to lower your maximum utilization for certain task sets. So moving to other classes of schedulers. So if you look at DR, I'm actually going to jump. So there's DR, DF, and SF. So here I have just a bunch of examples for you. Let's look at DR. So DR means the scheduling is, the priorities are dynamic. So each job gets its own priority. And you have restricted migrations, meaning that you can assign each job to a certain CPU. This would be suitable for task sets in which each job has a considerable amount of state. So if you assign your job to a CPU, moving it to another CPU would introduce a lot of overhead. So if you remember, we talked about memory footprint of our threads and tasks. And we talked about if I migrate a task or if I migrate a job, it's going to take time for the, let's say, caches to warm up to have the data that this job has. So if you have jobs that have huge memory footprints, you might want to focus on DR-based schedulers, where once a job is assigned to a CPU, it cannot migrate. You can look at DF for another example. So with this one, let's assume that you have a global EDF, a scheduler. So let's say all your jobs go to the same queue. So this is the same queue for all jobs. And then you have your CPUs. Now you can sort your jobs based on their deadline. And whenever you have a CPU available, you can give them to that CPU. So this scheduling would be a DF, because each job has its own priority, and because you're sorting them based on deadlines, if a job comes with a lower deadline than a job that, let's say, is running here, you're going to preempt the job. Let's say you're running job 2 from task 1. So T1 task 2 you're running, sorry, T1 job 2, and let's say T3 job 3 comes with a deadline that is less than T1.2, then you're going to preempt this guy, put T3.3 there, and bring back this job to your list. And next time that you might schedule T2.2, you might schedule it on another CPU. So basically, your jobs are moving between different CPUs. That's why you have F here. Another one that you could have is SF. So you could have a global RM instead of global EDF if you put an RM, rate monotonic scheduler for this single queue, then what you get is an SF. And you can actually show that the worst case utilization, similar to the one that we saw without migration, even if you allow migration, if you don't have FF, meaning you don't have fully dynamic and full migration, then the worst case utilization in your system is still m+1 divided by 2. So this basically about 50% utilization is the maximum that you can hope for certain jobs, certain task sets. Now, for FF case, where you have fully dynamic and full migration, then you could think of putting the same, the same single queue for all CPUs and put a global LLF to basically laxity, least laxity first scheduler for all of them. Now, this is FF, but it's not going to be optimal. So it does not provide optimal a schedule for you. So at this point, you might think, is there any hope to get to this 100% utilization? Basically, can I, if I have M cores, can I get all the way to M utilization for my task set? The answer is yes. So there is a scheduling policy called P-fair scheduling, which allows you to utilize all your CPUs to the max, which is M, for M CPUs. Now, unfortunately, I don't have time to go through this P-fairness. I have included the slide, sorry, the paper, if you're interested in knowing more about P-fair. So I just mentioned that it exists, and I'm going to leave it at that. So if you're interested, definitely look at the website, and there is a link included on the website on P-fair scheduler, so you can read it, or just look at my slides. I'm not sure if I ever got time to cover this in previous. I think one term I actually covered P-fair scheduler, only one term, if I remember correctly. The rest of the terms I had to skip over it. But anyhow, the idea is very cool. The only downside is that P-fair scheduler is expensive to produce a feasible schedule. It requires a lot of work. So that's the only downside of P-fair, but it exists. So there is some hope that we get to use all our CPUs if we have a multiprocessor running a real-time operating system or real-time system. Okay, so I'm going to jump from all of these. So again, overall, it has high overhead in making scheduling decisions. So that's the downside of this. And there are some, improvements on P-fair scheduling. There's PD, PD2, ER fair, and these are scheduling policies that are proposed to deal with the shortcomings of PF scheduler. Okay, so in summary, we looked at different real-time systems. We looked at why general purpose operating systems are not enough to run a real-time system. In particular, we looked at memory management. We looked at interrupt handling. We looked at the scheduling policies. We also talked about real-time scheduling algorithms like rate monotonic, EDF, LLF, and eventually we talked a little bit about the difficulties of running a real-time system on a multiprocessor. Okay, so with that, we're done with the real-time systems, and we can start talking about address translation. So I have to actually change the schedule because we weren't able to start address translation on Friday. Okay, so let's open it up. Yes, download. Okay, so the next topic that we're going to talk about is address translation. So I'm going to be fast. So each application. So let's actually look at what we have done so far. So far, we started with trends in hardware as our introduction. Then we talked about 4 concepts of operating systems. Then we moved on to implementing multi-threaded operating systems. After that, we talked about scheduling in uniprocessors, scheduling in multiprocessors. Then the last topic we covered was operating real-time systems. Now, the next topic that we're opening up is memory management. Now, similar to CPU scheduling, when it comes to memory management, we want to create an illusion for our processes. So each process has its own virtual memory address space, which is kind of infinite. I mean, it's finite, but let's say you have a system with 64 bits. Your processes can address 2 to 64 bytes. And this is a huge amount of memory. So you could imagine that this is like kind of like, I don't know, I think this is more than the number of atoms in the universe. So you have huge amounts of virtual memory, but in your systems you have limited physical memory. Your system has 4 GB or 8 GB or maximum 32 or 64 GB of memory. So you have limited physical memory, but each process thinks that it has infinite memory. So the job of memory management is to provide that illusion, provide the illusion that each process has an infinite amount of memory that it can access in a protected way. Very similar to scheduling. So with the scheduling, we wanted each thread to think that it's running on a dedicated CPU. In reality, we had limited number of CPUs and we had to time share. Now we're going to do the same thing. So we're going to multiplex memory so that each process thinks that it has access to unlimited amount of memory. There are 2 goals with memory management. The first one is protection. So we want to protect the kernel from user programs and user processes. We want to also protect user processes from each other. We might want to allow processes to access data, but with different permissions. For example, we might want to allow a process to read certain data, but not be able to write it, or write to certain memory region, but not be able to execute. So we want to have different access permissions to different regions of memory. Now, on top of protection, kind of like somehow opposite to protection, we also want to allow sharing. So we want to have protection, but a relaxed protection that allows processes to share data. And you have seen examples of memory sharing in 252, and also in the past lectures I mentioned certain things that would require memory sharing. So let's just look at a few examples. So one example is when you fork. If you remember, the child and the parent, right after a fork, they share the same memory. We don't make a copy right after we fork. We allow both of them to read from that same memory. The moment one of them wants to write, then we make a copy. So in this case, two processes, the child process and the parent process, are sharing data. So that's one example. The second example is inter-process communication, IPC, through shared memory. So if you remember, process A could ask from operating system to allocate a shared memory space, and then other processes could also use that memory to communicate with process A. So that's another example of memory sharing. Another example is memory mapped I/O. So usually when you want to use I/O, when you want to read, write, open your files, you use system calls that we saw. So you say open this certain file with this certain permissions. That's a system call. The operating system goes and does what you want from it. So reading and writing to and from a file is done through system calls. Now that's fine, but it's slow. Another option you have to read and write from files is through memory mapping. So there are certain system calls that you can use that would map a file to a region of memory. Once the mapping is done, then you can just use load and store instructions to read and write to and from that memory region. And doing this is as if you're reading and writing to and from that file. There is a caveat to this, because what you're doing if you're using load and store, everything is being written. If let's say you're storing, if you're writing to your file, everything is written to memory because this file now resides in memory. So at certain points in time, you might want to flush whatever you have written to the disk. So you would, at certain points, tell the operating system that now make a copy of this file, for example, in the permanent storage. Because if you, let's say, if you have a power outage, then your entire update is gone because all of the update was done in the memory. Now, with this, if two different processes want to share the same file, then they can both map the file to memory, and it's wasteful and somehow impractical to have two copies of this file in memory. So the operating system keeps a single copy in memory and allows both of the two processes to access the same file. So that's another example where you have sharing between two different processes. The last example here is user-level system libraries. Let's say CLib library or any other library that you have in your system. You don't want to copy multiple copies of the same library in memory because that's wasteful. You usually have the same copy in memory and then you map that same library into different processes, virtual memory. And this way, all of them are sharing the same physical memory to use the library without making multiple copies of the same file or of the same library. Okay, so that was protection, which was the first goal of memory management. The second goal of memory management is allocation. So you not only want to protect your data, you also want to manage and allocate available physical memory between your processes. The sub goals of memory allocation is basically you want this to happen efficiently. You don't want to spend so much time in deciding what the next decision should be when it comes to allocating memory. You want to avoid memory fragmentation, and then you want to, this last part we'll talk about later on, you want to be able to evict memory efficiently if you don't have enough space left, to evict pages back to this permanent storage, and then open up some space for other processes to use memory. So these are sub goals of memory allocation. Now, a little bit of background in terms of basics of memory management. So this first part is unrelated to memory. It's very basically discrete math. So if you have k bits, how many different things can you address with k bits? So each bit can be 0 or 1. So for each bit you can store 1 or 0. Now you have k bits, so that's 2 to k different numbers you can store in k bits. So you can have 2 to k different things, different numbers stored in k bits. And if each one of those numbers is an address for something, then you can address 2 to k things. Now, when it comes to memory, the thing is basically byte. So what we want to address is bytes. So each byte has an address. Now, if your system is 32 bits, then you can address 2 to 32 bytes. If your system has 64 bits, then you can address 2 to 64 bytes. So the unit of addressability is byte when it comes to memory in most of the systems. What is 2 to 10 bytes? Well, 2 to 10 bytes is called 1 kibibyte. And you didn't hear it wrong. It's kibibytes, and you write it as KIB. So there is this I there. And it's different from kilobyte. So if you say KB, that's 1,000 bytes. So 1 kibibyte is 1,024 bytes. Now, I'm going to stop using kibibyte, so I'm going to just say kilobyte. The same with megabyte and gigabyte, so it's gigabyte or something, or megabytes. I actually have forgotten what the terms are for, but it's right. It's written MIB and GIB rather than gigabyte, which is GB, and megabyte, which is MB. So this one is 1,000 kilobyte, and this one is 1,000 megabyte, whereas gigabyte is 1,024 megabyte, and megabyte is 1,024 kibibyte. So I'm going to stop using kibibyte, gigabyte, and stuff. So I'm going to just say gigabyte and megabyte, but please note that I don't mean this one. I mean this one. For just simplicity, I'm going to call it megabyte and gigabyte and kilobyte. But what I mean is 2 to 10 bytes, or 2 to 10 megabytes, or 2 to 10 gigabytes. Okay. How many bits do we need to address 4 kilobytes? So if you have 4 kilobytes, that means that you have 4 times 1 kilobyte, and 1 kilobyte is 2 to 10 bytes. So that means 2 to 12 bytes. In order for you to address 2 to 12 bytes, you need 12 bits. how much memory can you address if you have 20 bits or 32 bits or 64 bits? So for 20 bits, it's going to be 2 to 20 bytes. So that's 1 megabyte. For 32 bits, you have 2 to 32 bytes, which is 4 gigabyte. And if you go to 64 bits, that's going to be 2 to 64 bytes, which is 2 to 24 terabytes, which is 2 to 14 petabyte, which is 2 to 4 exabyte. So this is something that we call infinity. So this is like, you know, above anything that we can imagine, how much memory this is. So a system that supports 64-bit address bus can address 2 to 64 bytes, which is basically 16 exabyte, which is huge amount of memory that we will never have. So so this is basically your virtual memory, and your physical memory is always you know, orders of magnitude, actually hundreds of orders of magnitude less than this. A recall from the past. So we talked about address space. So address space is basically any possible accessible addresses and what they actually hold. Physical memory is a data storage that you have in your system, and physical address is the address space for your physical memory. So if you have 4 gigabytes, let's say, of physical memory, that means that you have 2 to 32 addressable bytes. Virtual address space is the address that your programs produce. And if you have a 64-bit system, that means that you can produce the number that we saw in the previous slide. I think it was 16 exabyte of memory. Let's look at the steps that happen when you run your program. So all the steps from writing your program until you execute your program. So after writing your program, you have a source code, and you might have different source codes. So different files, different source codes for each file. Now the compiler gets a source code and creates an object module from your source code. Now you have to be careful because your compiler doesn't see other source codes. So at any given time, your compiler is working with a single source code file. So it only sees whatever code is available in that single file. This means that there might be external objects, external functions, for example, like printf, that you're using in your code, but the compiler doesn't have the code for printf at the time that it's compiling your source code. So it creates some object table that has the name of the objects that are used, and the address for those objects is not filled. So they have to be filled later on. So there might be objects that you're using in your source code that the compiler doesn't know where they are. The other thing is, at the time that you're compiling your code, you don't necessarily know where this code will be loaded in memory. So compiler cannot produce end addresses for everything, right? Basically for nothing, because it doesn't know where each code goes. So everything is kind of like relative, the addresses that the compiler produces. Next step is linkage editor. So linkage editor gets bunch of object modules. So let's say you have compiled bunch of files. Now you get all of them. Now you might have you know, other modules that you have compiled in the past. You get them, you add it to the module that you currently have, and the linkage editor produces a single relocatable executable image. So this could require some reorganization and rearrangement of virtual addresses, right? Because when the compiler compiled a single source code, it only arranged the code, the data in that file, in that source code. Now, if you're merging bunch of object files, each one of them has its own code, each one of them has its own data, and so on and so forth, then you probably want to put all the code in one place, all the data in one place, and so on and so forth. So there might be some rearrangement across different objects. But at the end, the linkage editor produces a single executable image. Now it's relocatable because, again, the linker also doesn't know where this is going to go. So everything should be relative so that we can basically put them in different positions in the memory. Next is the loader. So this is when you are getting ready to execute your code. So at this point, you get your executable image and you bring it to the memory. So this would require the linker, which is the loader, sorry, which is part of the operating system, to allocate some memory for this image, and then copy the image to the memory, and then eventually transfer the control to the beginning instruction in this image. So at this point, you might actually need to also look at system libraries that you're using in your code, and then load certain libraries that your code depends on them as well. Now, the last step that sometimes is necessary is dynamic linking. So there are certain library calls that you might have in your code. For example, the printf that we saw, that you wait before you link it to your executable image. Because, maybe I have this if flag equals 0, then printf something. Now at compile time, I might not know if this flag will be 0 or not. So I might not even need to execute printf, and I wouldn't know this until when I start executing my code. At the time that I reach this point, if indeed flag was 0, and if indeed I needed to execute printf, at that point the dynamic linkage happens. So the operating system looks at the code for printf wherever it is in memory. It might not be in memory, in which case the operating system has to bring it to the memory. And if it is in the memory, then at the time of usage, you link it to your executable image. So if these are usually for shared libraries like clib, for example, where you have the printf, for example, or your other clib library functions. So you basically don't link them to your executable until the execution time. When the execution happens, then you look at the libraries. If they're not in the memory, you bring them. If they are already in the memory, you just bind them to your executable image. Now let's look at again, as a recall, let's look at the address space and address layout of a C program. So the binary was at the bottom, initialized, uninitialized, then the heap, the environment variables, and the stack. And And then eventually it was the shared library. So as you can see here, this is where the operating system is gonna bind the shared libraries. So at the time where you execute the code execute the code from the shared library, the operating system finds a region in your virtual memory address space that is free, and that should be between your stack and heap because that's the free region. So it finds a region there, and then it binds that region to the shared library that exists in the physical memory. And then every time you access an address here in your virtual address space, because it's mapped to the library in the physical memory, then you can actually run the functions from the shared library. If you remember again, for every single instruction that we execute, we have to go to memory at least once. So the execution cycle includes fetching the instruction. So you have to go to memory to read your instruction. Once you read your instruction, you have to decode your instruction. After you decode your instruction, you execute it. Once you execute your instruction, you might need to write data or read data from memory. And then finally, you update your PC. So you look at the next PC. That next PC might be next instruction, or it might be jumping to somewhere else in the code. Maybe it's a function call, or maybe it's a loop. It's a for loop. You have to go back to the beginning of the loop, for example, and then you repeat. So what does this mean? This means that at least one access to memory per instruction. So at least one time per instruction, we're going to go to memory. So, and in some cases twice. So in all the instructions, we have one instruction reference, and in some instructions, we might have data references as well. Now, if you remember when we were talking about the history of operating systems, the first kind of operating system that we talked about was uni-programming operating systems. So in this case, you had at any given time, your operating system was executing a single program at any given time. So in this setting, there is no point in having having protection, right? Because there's only one process in the system, and the operating system is kind of like non-existent in uni-programming. The operating system is usually basically just some system library to facilitate execution of your program. So this is basically the layout of physical memory in uniprocessor. Basically, the entire address space, the entire physical range of addresses are available to your user process, because your user process is basically the only thing that exists in the memory, with operating system being there. But again, looking at early operating system in uni-programming model, the operating system was almost non-existent because there was nothing to be managed, right? It was just a bunch of system libraries to facilitate the user process. So in early systems, there was no notion of virtual address. Basically, virtual address was equal to physical address. They were the same. And each program was able to access the entire physical address space. I'm going to actually stop here. So we'll on Thursday, we'll start talking about the multi-programming operating systems. And after that, we'll just talk about modern operating systems where you have virtual memory, physical memory, and then a translation from virtual addresses to physical addresses. Thank you so much for sticking around, attending the lecture. Thank you also to those of you who are watching this offline. Take care, be safe. We'll talk to you on Thursday. Bye.